Okay, I think we'll get started. So this is the first lecture in General College Physics. This is a non-calculus based course. And if you're coming from the GNL project, I really encourage you to look at the intro to this playlist just to make sure this is the right series for you. The emphasis here is more on my class at Concordia College. If you're coming from the class at Concordia College, then as I'll probably say in every single video, these can be helpful for studying it, or if you happen to have to miss a class, but I would really encourage you to continue to come to class. We will have a lot of in-class stuff, so not everything that we'll cover here will be the experience you'd have in class. So definitely try to get to class for sure. Okay, so a good place to start with General College Physics class is the question of what is physics? And to answer this, we have to go back a little bit, well, actually quite a bit, to the Big Bang. And so at least 13 billion years ago, we're maybe thinking even more with the new information coming in from the James Webb Telescope that the universe started with about 13 billion years ago, or a little bit later with the Big Bang. In that very early instance, there was a very rapid expansion of space and time itself. This was called the inflationary period. In that expansion period, sort of a fingerprint of the universe was left on space and time as this expanded. This gave rise to an enormous number of particles, both particles and antiparticles. Many of those found themselves and annihilated each other in massive amounts of energy. But there were a slight imbalance in what we call particles versus antiparticles. And after that was all over, we were left with the current mass of the universe. As the universe cooled, the fundamental particles came together in protons and then the electron, and those would come together then to form hydrogen. And the early universe then was primarily hydrogen. It was not homogeneously distributed, it was heterogeneously distributed, meaning there were chunks of the universe that were higher in hydrogen. This gas then, because of the very weak but present gravitational attraction, formed these nebulas that were the early cradles for the birth of the first generation of stars, which ran on fusion of hydrogen into helium. Some of these stars would die off in a huge explosion called a supernova that would create the heavier elements in the periodic table and spew them out across the universe. Well, the cycles and later generations of stars have not only the hydrogen, but also the other elements of the periodic table. Our solar system arose, and there was enough other material for the planets surrounding our sun. So about 4.5 billion years ago, the Earth formed, and in relatively short order after that, things settled down enough. There was a lot of chemistry happening. There was plenty of energy there to supply that chemistry. Likely or possibly all inorganic, very small nanoscale inorganic particles that were in the ocean sort of created this, or attracted these organic molecules around them in this halo, and then either with lightning strikes or near hydrothermal vents, there was energy there to do some chemistry. Some of that chemistry was such that the molecules would reproduce themselves, so sort of a prebiotic type of behavior. Then eventually, this organized itself into sort of a sac that we would sort of call a cell, and inside that cell were the various chemical machinery. Now, an alternative view is that the fabric of life, the chemicals of life came from outer space. So there's sort of two competing views, and an asteroid hit seeds the Earth, but this is an Earth like an earth up idea. Well, as time goes on, opportunistic bacteria or archaea incorporate each other. So maybe a bacteria that's specializing in photosynthesis, or one that's specializing in metabolism, gets incorporated into other bacteria or archaea to produce a more organized cell, or a prokaryotic cell, with a mitochondria and perhaps a chloroplast for doing photosynthesis. Well, these cells then eventually become more complicated, string together into multicellular organisms, and so we have the birth of the eukaryotic cells and the multicellular organisms that slowly evolve over time. Then this was punctuated by a very rapid advancement called the Cambrian explosion, where there was a massive diversification of life in the Earth's oceans, and which gave rise to ultimately the fishes that some of them, some ambitious fishes would kind of creep out onto the shore, and slowly the fins developed into legs, and we had the rise of the amphibians. Then along came the reptiles, and of course the most dominant of these are the dinosaurs that ruled the earth from about 220 million years ago to the fateful 0.66 million years ago, when an asteroid struck the Earth and caused a massive extinction of those dinosaurs, freeing the way for the little mammals that were already starting to scurry under their feet to rise and be one of the more important species on Earth. As the mammals became more complex, the primates arise. About 6 million years ago, the chimpanzees and bonobos split from the Homo species. So we have Homo habilis, Homo erectus, Homo neanderthal, Homo denisovans, Homo sapien, sort of all mixed together, and all but the Homo sapiens die off, leaving us, which become one of the most successful species in terms of dominating every corner of the earth. The reason for that was the remarkable ability for us to be able to communicate with one another, which allowed us to form social systems and cooperate. Along with the social systems came an ability to abstract away and reason and logic and look beyond the most immediate, which gave rise to mathematics, both with the Babylonians, the Chinese, and with the Greeks. And so this idea of logic and reason and mathematics built up, and then was maybe after sort of a dark period, then in the late 1700s, Newton, with the invention of calculus, along with Leibniz, Newton writes the Principia, which is really the foundational first physics book in a sense, and the birth of sort of what we call physics, which is a systemized way of looking at this grand story of the formation of the universe, the formation of the planets, the evolution of us, and our ability to then look back and study this critically and gain an understanding of where we came from, one of the most fundamental questions for humanity. So that's a grand story, and physics is the science that tries to look at this in a very systematic way by trying to explain nature with very clear and explicit concepts. And what that allows us to do then is be able to describe nature logically and mathematically. So we try to take simplified models, try to understand what's going on with nature, and then be able to cast the discussion of that sort of back and forth between, say English or French or German or whatever, and mathematics. So this language of mathematics talking about physics. This mathematical description then allows us to build from so-called self-evident concepts like gravity and idea of position and motion to concepts that are quite unintuitive. So it allows us to carry ourselves into areas that we can't perceive most directly. And one, that explains results, but more importantly, it predicts results and allows us to predict things about the grand cosmos, which we cannot reach, and the microscopic, the world of chemistry. And so this is what physics allows us to do. So that's, of course, sort of the grand story of what physics is. But now comes the hard work of getting down to the business of learning how to do physics. So that largely means translating between this English and math, and from what is the math telling us, what does that tell us, how can we then gain an intuition about how nature works? And so we have formula that we're going to work through. We're going to try to understand concepts, be able to solve problems. All right, well, one of the things that we're going to do, and what has helped physics organize itself, is that there are certain fundamental symmetries in nature. And this is captured by Emma Noether's theorem, and she proved both in the forward direction and the backwards direction, so the theorem and the converse of the theorem, that every conservation law, and so certain very special properties, momentum, angular momentum, and energy, these are all core topics that we'll be getting through even in this first semester, correspond to some kind of symmetry in nature, and the converse. If there's a symmetry in nature, then there must be a conservation law for that. Now, we won't go into the details of Noether's theorem, one of the sort of the standard theorems of so-called mathematical physics, but just as sort of a rough idea, and this is not certainly not exact, but how I like to describe it is the idea that if I'm doing physics here, the laws of physics are the same as you doing physics at a different distance, at a different position. Now in your study, the laws of physics are the same. And so there's a translational symmetry there. And that translational symmetry of nature, then connected with that is a conservation law, the conservation of momentum. And then this idea of if we do physics today, or tonight, and then tomorrow we go and do physics. Earth has rotated. We have rotated in space, but the laws of physics are the same. So we have a rotational symmetry, and that is connected to angular momentum. And then finally, if we do physics today and we do physics tomorrow, the same laws of physics apply. And so there's a time symmetry, a fundamental time symmetry in nature. And that gives rise to the conservation of energy. And so these three properties, there are a few other conservation laws, but these three are the main that physics are built around: momentum, angular momentum, and energy. Now, to get there, we have to introduce a lot of concepts, and we're going to start with very familiar ones today. We'll talk about position, and we're going to talk about velocity and speed. So those would be the first concepts that we're getting to on our trek through this understanding of physics. Now, regarding that, we will be solving problems always not using calculus. This is a non-calculus based physics course. And while that might seem as a limitation, you can do an awful lot of physics without calculus, but there are certain things that definitely calculus is the more natural language for, and in fact, we'll see that today. So what I will sometimes do is take just a very quick aside to say, if you've had some calculus, this is what we're seeing. And if you haven't had any calculus, just kind of relax, wait, and come through the other side for that. But I think for those of you who have had calculus, sometimes seeing how it's connected to what you've learned in calculus actually helps with the insight. Okay. So how do we approach a problem in physics? Well, that's going to be something we're going to be working on, and today we'll get started with that. And we're going to just look at the first couple of steps here. First thing we do when we come to a problem is we want to know, what do we know and what do we want to know? And then the trick of it is, can we find a path of things we know how to do to get from what we know to what we want to know? So the example we'll go through in just a bit is dropping a ball off a roof, right? So we can't solve any equations yet or anything like that, but we want to set this up in this way. So what do we know? Well, we're on this roof, say maybe it's 10-meter building, and we want to drop this ball. And we want to know, then what do we want to know? Well, it could be many things, but maybe one of the things we want to know is how fast is the ball moving when it hits the ground? What is the speed when it hits the ground, or what its velocity when it hits the ground? So that's the physics problem. What will help you immensely is if every time, unless you see the path perfectly, every time draw a picture. Try to draw a picture of the physics that's going on there. And it can be just a rough sketch, but you want to capture the essential aspects of the problem. And we'll go through that with this ball drop example. And then we want to establish a coordinate system. So we'll be talking about a coordinate system here. Coordinate system can be a 1D coordinate system, 2D, 3D, and then there's also time that comes in there as well. We can do a fair bit of physics in one dimension, but you really need 2 dimensions to kind of get a lot of the variety. And then for a very few things that we'll do throughout the semester, we do need all 3 of the dimensions we live in. Not too many things do we need that. And so we'll be doing a lot of our physics just in 1 and 2 dimensions. Certainly this beginning material will be that way. And then there's more to come. So this is not it. There's more strategies that we build on top of this to solve problems in physics. All right, so I'm going to erase the board now and go through the example of the ball drop, and then we will go through talking about velocity and speed, position, velocity, and speed, and then we'll end with just a brief discussion on physical quantities. Okay, let's pick up with that ball dropping example. So let's say we had the problem of we're on this 10-foot building and we're going to drop the ball, and we are going to try to figure out what is the speed or how fast is the ball going when it hits the ground. So what we know is we're on this building 10 meters. Where we're trying to go is how fast is it going when it hits the ground. Our first step is to draw this cartoon picture. So we draw this building, and here we are. And we're going to drop this ball down to the ground. Right? So this captures the essential physics of what's going on. It doesn't matter what there's grass on the ground or there's windows in the buildings. What we're really interested in here is what's going on here with the physics. So we might want to then decorate this a little bit with the fact that this is 10 meters, right? Just to kind of bring along any of the given information that we're told. Well, now the next step is to set up a coordinate system. Now when we set up a coordinate system, we have freedom. We can choose the 0 of that coordinate system any way we like, and our friend could choose a different 0. Oftentimes in a problem, and this is what the picture helps you with too, there's a natural place for the 0, or at least a couple of natural places for the 0. In this case, there's 2 natural places for the 0. One is we could define the 0 down here, and we'll just call this Z. You could call it X. Actually, let's go ahead and call it Y. In a 2D physics that we'll be doing most often, up and down is going to be Y, left and right is going to be X. In 3D, usually up and down is Z, and then this is XY direction in these directions. But we'll just call this the Y direction here. Okay, so I could define my 0 here, and that would be 0 meters right there. Then we know, once that's defined, then we know this ball starts at 10 meters. And the convention is up is positive. And down is negative direction, so it gets lower as we go down. So maybe I shouldn't say positive. Up gets bigger. Or we could say the positive direction is the upward direction. Up gets bigger, down gets smaller. Okay, so this is one perfectly good coordinate system. But your friend might come along and put the ball at 0, right? Perfectly legitimate to do that. And then this would be minus 10 meters. Now note here, if you were to ask the question, what value is the ball at? You would say 10, your friend would say 0. That is not the essential part of the physics, right? It seems like you might be getting different answers. But whenever we're addressing a problem in physics, the coordinate system ultimately doesn't matter, because the question is here, the physics is about this ball traversing from here to here, which regardless of whether it's you with your coordinate system or your friend, the ball has moved 10 meters downward, or minus 10 meters. Okay? And so the choice of 0 really is up to you. And again, you look for natural important ones. You could put it right here, but that'd be kind of a silly place to put it. Okay, well, similar to the up and down, we're talking about position. So here, the position is in the y direction. Here's our x direction over here. And we denote the position as the position vector, right? And we'll talk a little bit about what a vector is here coming up. But briefly, a vector is something with a magnitude and a direction. So let's say we've got our point here. We represent a vector with an arrow. So we would say that if we're sitting here, if this is our point, right, we are at 2 in the positive direction, right, or to the right. So we would say x equals plus 2, right? Or we could say x to the right. Well, let me not write that for now. So plus 2. If we have a different vector here, and we're sitting, our position here, we're sitting at minus 2. So let's say we're sitting over here, then we would say our vector is minus 2. Okay. In both cases, our distance between here and here is 2. So the magnitude of this vector is 2, but the directions are opposite. And the convention is, much like here, if we go to the right is in the positive direction or increasing direction, and to the left is in the negative or decreasing direction. All right, so that's position. We're going to talk about velocity today. We're going to keep adding different terms here. So velocity, it will be our last term for today. And so let's imagine a car here that we take a kind of a snapshot of it right when it's at position 1. So we talked about position up here. And then it's going to move along this coordinate system to position 2. So we're going to go in this direction here. And then we'll take a snapshot here at position 2, and we're interested in what is the car doing between 1 and 2. And what the question we're going to be interested in is, what is the velocity of that particle, or of that car? Okay, so how do we define the velocity? It too is a vector, and what it's doing is it's saying, okay, if I go from position 1 to position 2, I have a change in position, x2, and now this is as a vector, right? So this is just the points on the coordinate system, but this is sitting, if this is 0 over here, this is 2, and this is 1. So it's this vector minus this vector, right? Magnitude and direction. So in this case, well, we don't know yet. I mean, these could be negative numbers as well. So just x1 and x2. But it's final minus initial. And it does this in a certain amount of time. Time is not a vector. Time is just a single value, and that is t2 minus t1. So the t1 and the t2 are not so important. That just depends on when you define your 0. But what matters is the difference. Same with position. The physics of the problem is the car moved this difference in position. It doesn't matter what these values were. What matters is the difference. Same with the time. So then we can take the change in position with the change in time. And if you've had some calculus, velocity is actually dx dt. But for us, we'll be talking about discrete changes. So change in x with change in time. And that's the velocity, right? So that's going to have a direction. If the car is going this way, then the velocity will be a positive value. If the car was going this way, it would be a negative value. And the magnitude of that vector is what we call the speed. So the speed could be 5 miles an hour, but is it to the left, is it to the right? It doesn't carry that information. The velocity is 5 miles an hour to the left or 5 miles an hour to the right. How these interchange is, we could say velocity is minus 5 meters per second and be done with it. Or we could say the velocity is 5 meters per second to the left, right? We have to decorate that magnitude or that speed with the direction, either in words or with the sign. Okay, that's a little bit confusing at first, but always think about velocity as a magnitude and a direction. You can think about speed as just a magnitude. And so that brings us to a bigger category of the different types of physical quantities. We've seen both of them here now that we're going to run into, and that is a vector, so that has a position and a direction. And then we have what's called a scalar, or just a regular number. And that is like the speed. Right? And another good example is like weather information. So imagine, across the state of Minnesota or across the globe, we've got weather stations, and at each weather station it might be measuring a temperature. We don't say like 30 degrees to the north or 30 degrees to the east. It's 30 degrees, and that is that's a scalar. The wind direction, or the wind, we might say, is 10 miles an hour out of the north, or 5 miles an hour to the east. And those are called, those are examples of vectors, because they have both a magnitude and a direction. That's all we're going to run into. There are a couple of other things in physics. Tensors, these are things that engineers are really worried about. Chemists are worried about tensors and spinors. These get into the real fundamental properties of electrons. And so we won't run into those, but this sits in a broader category of these sort of physical quantities. All right, the last thing, which we won't do here, but we'll do in a practice worksheet, is in class, and that is let's really get good at our brush off the rust from our triangle trigonometry and geometry. So Pythagorean theorem, really important, and then the SOHCAHTOA, sine, cosine, and tangent, how that's related to the sides and hypotenuse of a triangle. That is very much related to a vector. So we're going to practice that, and also just working with vectors. All right, so that's that. And so again, if you're coming from the GN Lewis project, hopefully this was enough for you. Go back and watch that intro video to make sure this is the right course you should be looking at. Concordia students certainly come to class, and we'll work on those practice worksheets.